Hi again, everybody. Again, I'm Kathy Zip, Managing Editor of Solar Power World, and I'd like to welcome you to today's webinar, Battery Backup for Grid-Tied PV Systems. And we would like to thank Simple Ray Solar for being our webinar sponsor today. And before we begin, we'll go over just a few house cleaning items. I'd like to mention that this webinar will be available after the presentation on solarpowerworldonline.com, and it will also be emailed to all the registrants. We have a lot of questions about that, so you will be able to view it again at your convenience. Secondly, there will be a question and answer session at the end of the presentation, and this is a great way to pick our presenters' brains, so we encourage you to participate. You can do so by submitting your questions whenever they come to mind, at any time during the presentation or after, by typing them into the GoToMeeting panel on your right. And lastly, we encourage everyone to tweet about key topics and discuss takeaways using the Twitter hashtag #SolarWebinar. And at this time, I'd like to introduce our presenters. Today, we're thrilled to have Doug Pratt, Senior Engineer at Simple Ray Solar. So we'd like to extend our thanks to Doug for being here with us today.
Okay, well, I think that we had lost Kathy there, so I'm going to go ahead and hand the controls over to you, Doug, and let you go ahead with your presentation.
I'm back. For some reason, I lost the call there.
Okay, I'm going to go ahead and hand you the controls and let you kick off your presentation.
Okay. Good afternoon, everybody. This is Doug, and welcome to this presentation on battery backup for grid-tied systems, and happy Earth Day. I feel honored being able to present on Earth Day. Wow, pretty cool. Okay, so let's move along here. First, we want to give it a moment of thanks to Northern California growers. No, not for the things you're thinking of. A curious thing happened back at the beginning of the PV age. All through the 90s, or 80s and 90s, better than half of the PV sold in the US ended up somewhere between Santa Rosa, California, and the Oregon border. It was, the growers who could afford PV back when it was better than 10 bucks a watt. These folks were living off the grid, out in the boonies, and many of them were already living on 12-volt systems back then. So when PV first came out, they embraced it, and they could afford to buy it. So to a great degree, it was the growers early on who financed the beginning of the PV industry. An amusing side note, everybody loves that one. Okay, so let's think of electron flow from a PV array much like water flow. You either have to put it someplace or you have to shut it off. So our household loads, our utility grid, batteries, these are all places that we can put electrons coming out of the PV system. They got to go someplace. Back before about 1995, all PV systems were battery-based. There wasn't any grid-tie. Grid-tie didn't come around until about the mid-90s. And even when it did, the first grid-tie inverters came from Trace Engineering, and they were all battery-based. Eventually, we learned how to treat the utility grid as if it was a great big battery, and the direct grid tie systems were born. That's when sales really started to take off, when we could build these systems without batteries, tied to the grid, you know. So direct grid tie is simpler, it's cheaper, it's more efficient, and it quickly became the dominant force in our industry. You know, now we got lots and lots of installers out there who, you know, you may have years of experience, but you've never done a battery-based system, and therefore they're scary. You know, so whether it's battery-based or grid-tied, you always need some place to accept the extra electrons or supply the deficit when there's more demand than what there is supply. So in this example right here, we've got a PV system up on the roof here. It's got a battery pack, and it's got a connection to the utility grid. So this system can run either on the utility grid, or if that fails, it will automatically switch to backup batteries to supply household loads. And that's the sort of system we're going to talk about today. So, what's usually the first question you get from your customers about battery backup? What's it going to cost? Okay, and we're going to be honest with you here. The additional retail cost to add backup to a standard grid tie system, this is for materials, labor, markup, you know, you're looking at $6,000 to $8,000 minimum. So that right there is going to discourage a fair number of your customers who are asking about, well, I want grid tie, but can I do backup too? The answer is no, backup isn't for everybody. You know, who really needs it? Battery backup is for folks who need instant, reliable backup. You know, think data needs, you know, computer support, and folks with medical issues. You know, those are the people who really need instant battery backup. For everybody else, this sort of system is convenience and bragging rights. In all honesty, your average residential client is going to be better and cheaper served with a generator and a large tank of propane. You can sell them that for, you know, $3,000 to $5,000, and that's going to get them through your typical 3 to 5 hour, you know, sort of utility backup, utility failure. And for those clients who insist on being able to run everything when the utility is down, generators are definitely the best choice. Battery backup systems are meant to only cover critical loads. By that we mean the fridge, the freezer, the furnace, water pressure, you know, if the customer's got their own well, a couple of lights in the security system. You know, those are usually the basics that we see getting covered by the critical loads battery backup system. Swimming pools, lights on the tennis court, and no. Air conditioning, that's negotiable. I have tried to convince people in Florida that they could survive without air conditioning, and apparently you can't. In Florida, air conditioning is not a negotiable point. So, hey, you know, it's the customer's system, it's his battery pack, you know, he can run it down as fast as he wants. So if they want air conditioning, yeah, we can cover it. But then, on the other hand, have convenience and bragging rights ever failed as a sales tool? you got a customer who's passed the dollar test for battery backup. You know, they didn't faint when you said, you know, $8,000. Okay. Now there's two paths to battery backup: the haves and the have-nots. Does the customer already have a grid-tied system installed, or have you already sold them a conventional grid-tied system that now they're saying, oh, but what's it going to cost to add battery backup to that now? You know, this is the most common type of scenario where the customer either already has it or wants it with their system. You know, we saw a lot of people after Hurricane Sandy inquiring about these sorts of systems, you know, to add on to their existing grid-tie system. So in this case, we've got add-on systems, either from Sunny Island or Magnum. The add-on system will disconnect from the utility when it senses utility failure, and then it will send an AC signal into the system, and it will fool the conventional grid-tied converter or inverters into thinking that the grid is still up. So the grid fails and the sun is shining, your conventional Sunny Boy inverter is going to keep running. The Magnum is a lower cost system, and it'll work with any brand of grid-tie inverter. The Sunny Island will also work with any brand, but it works better with Sunny Boy inverters. Sunny Island and Sunny Boy, both from SMA, will communicate with each other, and when the grid is down, the Sunny Island will actually take over control of the Sunny Boy inverters and will throttle them up and down as needed to meet the needs of household loads and battery charging. You know, if the loads are all satisfied and the batteries are approaching full charge, the Sunny Island will actually throttle down the Sunny Boys as much as necessary. Pretty slick. Sunny Islands will also do three-phase systems. We'll get into that a little bit later. Both the Magnum and the Sunny Boy will do conventional 120, 240 split phase. Usually the sub pumps are the most challenging load that we run into on these systems. They are a bitch to start. Heavy starting surge. So, you know, up to 3/4 horsepower pumps, you know, not a problem. 1 horsepower and larger, yeah, we can do that, but we may need to beef up the inverter pack to do it. So let's talk about it first. Okay, is this going to work right for me? Let's see. Excuse me while I play with the graphics here. Okay, SolarWorld's presentation software isn't working perfectly here. What we have here is a conventional PV array going to a conventional grid-tied inverter, in this case a Sunny Boy 2500. The output from the Sunny Boy would normally go straight to the household main AC panel. All right, that's the way you guys are used to wiring them downtown. With this backup system, what we've done is insert our backup system here in between. Now the output from the Sunny Boy, instead of going directly to the household main panel, it's going to a critical loads subpanel here and landing on it. The subpanel gets its power by way of the Magnum or Sunny Island here, by way, you know, which is inserted in between the main panel
and the loads here. If utility fails now, our new battery-based inverter is going to first isolate itself from the main panel. It's going to open a breaker and cut this off, open a contactor, and shut off any access to the utility. And then it's going to power up using stored energy from the batteries and supply power, continue supplying power to the critical load subpanel, where you've got all your supported loads. This, because the Sunny Boy is also connected to this, it'll see this AC power and go, oh, I thought the grid was down, but no, it looks like it's doing fine. Okay, I'm back up. So it takes about 30 to 50 milliseconds usually for this switching, disconnecting from the utility and then powering up. It takes a few milliseconds for that to happen. Probably our grid-tied inverter will notice that lag, and it will probably do a standard 5-minute timeout because of that. Depends on how the utility fails and all that, but it's typical that we will do a 5-minute timeout, and then if the sun is shining, it'll come back up again. If the sun isn't shining, well, we still got the stored energy in the batteries, and we'll support our critical loads. So these add-on kits will work with new or existing conventional grid-tied systems. Doesn't matter if it's a brand new one going in or if this is something that's been in place for years. You can go back and retrofit these. You don't have to do any alterations on the existing grid-tied system. Okay? The PV array stays the same. All the wiring going to the inverter stays the same. And any brand of conventional grid-tie inverter is okay with these systems. So let's look at specifics here. Your single Magnum add-on kit, the inverter will deliver about 4,400 watts, and that's 120, 240 split phase. We're limited to approximately 4,000 watts of PV input on this one. So be aware of that, okay? We can easily start any 1/2 or 3/4 horsepower sub pumps, and cost, now this is a wholesale cost, this is your dealer cost for this kit, is about $5,300. We can also offer a dual Magnum add-on kit. It'll deliver 8,800 watts. Now we're limited to 8,000 watts of PV. We can start up 1.5 horsepower sub pumps, no problem. Your cost is about $7,400. The Sunny Island systems are a bit more expensive. No, they're a lot more expensive. Okay. The SMA stuff is really good, but it's pricey. A single Sunny Island, it'll deliver about 6,000 watts into a load. We're limited to about 8,000 watts of PV. We can start 1/2 or 3/4 horse sub pumps, and your dealer cost is about $8,600. We can also offer a dual Sunny Island kit, and it'll handle up to about 12,000 watts. We can process as much as 15,000 watts of PV, and 2 horsepower or large or smaller sub pumps are fine. 13,500 for that one. These kits are going to include the inverter, an AC/DC power center with appropriate breakers, for input and output from these battery-based inverters, the DC cabling. We've got a sealed battery pack with about 9.5 kilowatt hours worth of stored energy capacity, and we've got battery boxes included with these kits. you need to install a locally supplied critical loads AC breaker panel. This is off the shelf, standard Challenger box, Square D, whatever your favorite brand is, supplied locally. And breaker panels locally supplied. And again, these prices that I've quoted here for the, for these systems, that's a dealer wholesale cost. I expect you to mark that up. Have-not systems, okay? In this case, we're going to start with a blank slate. There's no existing PV on the house, and the client says that they want to do a solar system with backup. These sorts of direct battery-based inverter systems are usually less costly than add-on systems. Depends on how fancy and big the customer wants to get, but we're usually going to be a couple $1,000s less, but it depends very much on how big the PV system is and how much battery backup they want. It's not unusual for batteries to be almost 50% of these system costs. So direct battery-based systems can be either off-grid or grid-tied. There are many battery-based off-grid inverters. Many. There are a few of them that are capable of grid tie. Outback, Schneider, formerly known as Xantrex, and Sunny Island inverters are battery-based and grid tie capable. These are the three major brands that can do grid tie for us and provide automatic battery-based backup. And I should note that not all Outback models have grid tie capabilities. They need special software loaded into them, and those models must have a G in the model name. Now, things get a little different with these battery-based systems. We're going to use a gizmo called a charge controller in between the PV array and the battery. Here's a basic schematic of the system. You got your PV array. Power from it goes to a charge controller and then to the battery pack. On the other side of the battery pack, we've got our battery-based inverter. And here we've got, AC input that goes to the utility grid and AC output that goes, again, to a critical loads supported panel for us. I've seen inexperienced dealers connect the output from the PV array directly to the inverter on these systems. Hey, that's what you do downtown, right? You wire up your PV array, and you connect it to your inverter. This particular dealer managed to toast a $20,000 battery pack doing this, because it was about 2 months before anybody noticed that there was a problem. I'm on a phone call with some guy out in the field one day, and he says, "Why does it sound like the batteries are always bubbling on this site?" And one thing led to another, and they hadn't even connected the charge controller. They wired directly from the PV array to the inverter, and they just toasted the batteries. Don't do that, guys. Okay, so the way these direct systems that work is we're going to program the charge controller and tell it, your job here is get these batteries up to 56 volts. At the same time, we've programmed the inverter and told it, don't let those batteries get above 53 volts. So the charge controller is finding all the PV energy it can possibly find out there. It's in maximum power point tracking mode. And it's shoving all this wattage into the battery pack and doing everything it can to get the voltage up to 56 volts. At the same time, the inverter is noticing the rising voltage, and it's grabbing that power, pulling it off the battery, converting it to AC, and shoving it out to the household loads and/or the utility grid. The inverter is injecting all that power right here, on the supported loads side of the transfer switch. This, by the way, is a built-in automatic transfer switch right here. We'll come to that here in a second. So, as I said, the inverter grabs the excess electrons, turns them into AC, shoves them out into the grid. Now, normally, as long as the utility grid is up, this internal transfer switch is going to be closed, and power can flow out of the inverter and it can flow out to supported loads. Once they're all satisfied, it can flow back this way and back to the utility grid. Also, it can go both ways out of this inverter. If the grid fails, this switch opens. Again, it takes about 30 milliseconds for that to happen. Now the utility is still, the inverter is still running. It's still making AC power, and it's still sending it out to the supported loads. There's been no interruption, no hiccup, nobody in the house has noticed yet that the power went out. So the utility grid is now cut off. We're not trying to power up the rest of the neighborhood. We're cut off from them. But the supported loads inside the house are still getting power. And that'll be, either from PV input or from our stored energy in the batteries. All the battery-based grid-tied inverter systems out there use this kind of system with an internal transfer switch that opens to cut off the utility grid. So Outback, Xantrex, Sunny Island, they're all using the same sort of system here. Now, this internal transfer switch is a bottleneck. Most manufacturers, it's a 60 amp unit, which means we can push 60 amps of AC through it. Well, that's not near enough to run a household, with the Magnums, actually, it's a 30 amp transfer switch. So, we got to be careful about what we choose as our critical loads. This is why these battery-based systems are not good at running the whole house. They are really for critical loads. So again, for those clients that really have to run everything, I got to suggest, a 15 to 20 kilowatt generator and a large tank of propane. It's a better solution and it's cheaper. Propane, by the way, makes a great backup source. It's usually delivered to site and it doesn't degrade with time. And hopefully it doesn't leak away. Okay, let's look at what's available for us in direct grid-tied battery-based inverters. For modest-sized systems, Outback makes a single GFX inverter model. It's rated at 3,600 watts. It's 120 volt only.
So if you got some 240 volt loads, like your sub pump, then we have to add a transformer to it. It'll start half or 3/4 horse sub pumps, and it is available pre-assembled as pictured here. Here's our inverter. Here's some AC switch gear hanging out over here. There's some DC breakers over here. Here's our charge controller. Here's monitoring here. This comes pre-wired, pre-packaged. You basically connect the batteries at one end, the AC at the other end, and the PV coming into the charge controller, and you're done. Outback also makes a dual GFX system. This has 2 inverters. The DC and AC boxes are much larger. We're talking about roughly 2 feet high by 5 feet long wall space here. Fair amount of wall territory here. The dual FX system will do 7,200 watts. It is 120/240 split phase, and it comes pre-assembled as you see. So, same deal. We're only allowed to use a max of 2 of the Outback GFX inverters on a grid-tied system. So 7,200 watts is our maximum input on those. Off-grid, we can go much larger. We can stack up to 10 of these in a single system. But on-grid, only 2 GFX inverters. So, you want to go bigger? Sure, we can do that. Outback makes the Radian series. This is an 8,000 watt inverter. It's split phase, 120/240. Built-in 60 amp transfer switch. Up to 1.5 horse sub pumps, no problem. Probably up to 2 horse, no problem, but be careful. And we can stack up to 10 of these in a single system. This picture you're seeing is 3 Radian inverters. So it doesn't have to be this big. Wall space, a couple feet wide, about 3.5, 4 feet tall. There is no pre-assembly available on these, unfortunately. You got to put them together yourself. Although you can get the AC/DC panel down here at the bottom. That does come pre-assembled for you. Other choices, the Schneider used to be Xantrex XW series. This is it's either available as a 4.5 kilowatt or a 6 kilowatt unit. It's also split phase. And we can start large sub pumps. You can stack up to 4 of these XW inverters into a single system. There is not pre-assembly available on these either. Sorry. Can we do 3-phase? Yes, it's possible. It doesn't happen real often, though. The only system that does battery backup for 3-phase right now is the Sunny Island. It tends to be sort of expensive, but it's very, very adaptable. With standard residential systems, we're limited to a max of 3 Sunny Islands on a 3-phase system. Now, SMA does make something they call a multi-cluster box, which allows us to gang up clusters of 3 Sunny Islands. And we can do that up to 4 times on a single system. So we get up to 12 of the Sunny Islands, all feeding a single 3-phase system. This sort of system is quite expensive. It's also kind of become the world standard for remote power systems. You know, islands, eco resorts, places like that. You know, a lot of remote sites that have been running diesel generators for power for the past 20, 30 years. Diesel has suddenly gotten horribly expensive, and it's killing these folks. And they're looking for any way to get off the diesel here. And the multi-cluster package has become the way to do that. We can do these systems. I've done several of them. They're a real big deal, but boy, when they're in, they work sweet. And if any one inverter fails, you know, the rest of them in the system just pick up the slack. You know, it opens the contactor automatically, cuts that problem inverter out of the system, and the rest of them just pick up the slack for it. It's nice. So, you know, the Germans are expensive, but they do things really well. You know, if this is not a full-time application, then, you know, we might look at backup generators. But like I said, there's a lot of remote islands that are, you know, looking hard at these sorts of systems now to get off the diesel. Okay, let's talk a little bit about battery choices for these, because it matters. Going really big on the batteries is not a smart thing to do on these systems. 1 to 2 days of battery capacity is probably prudent, sufficient. More than 2 days worth of backup storage, I got to say, is just foolish. You know, most utility outages are less than 4 hours. You know, batteries are very expensive and are becoming more so. And used or not, batteries are going to need regular replacement. 7 to 10 years is typical life expectancy. You know, we can get 12 to 15 years, you know, out of the best top of the line batteries. But even those are, you know, eventually going to wear out. And it's a rude awakening to system owners when they have to plunk down several $1,000s for new batteries. And they feel like, well, gee, I hardly ever used them. Oh. So, you know, for longer outages, you know, I'm thinking those of you that face winter ice storms or hurricanes, you know, where power may be out for a week or longer, a backup generator and a large tank of propane, you know, paired with the battery backup system is a great package. The customer can run off of the battery all day long. In the evening, he could start the generator for 3 or 4 hours, turn on all the lights, watch TV, burn power like crazy, and charge his batteries while it's doing all that. And then go to bed, you know, the next day do it all over again. So, you know, with 2 to 4 hours of generator runtime per day, we can stretch the system use out for as long as we need to. So, what kinds of batteries? Lead acid is the, you know, standard, been around for more than a century. But lithium ion, you know, we're hearing about all the time now. So lithium ion is a great choice when you need lightweight and small size. You know, we've been using them in our cell phones and our laptop computers for years now. We're starting to see them showing up in electric vehicles, again, where small size, you know, and lightweight are
real pluses. The problem is it's still 4 to 5 times more expensive than lead acid. So yeah, you can go lithium ion, we've got some choices we can offer you for it, but I'm not going to encourage it real hard. It's still a very expensive choice. For most of these systems, it's going to be lead acid batteries. Now we've got a choice between the wet cell batteries or sealed batteries. And among the sealed types, they make both AGM types, absorbed glass mat, that stands for, or gel types of sealed batteries. Well, all those lead acid batteries need some exercise in order to stay healthy. The sealed batteries, and particularly the AGM types, have had their chemistry tweaked to tolerate long periods of float charging, inactivity. And that makes them ideal for backup systems like this, which are typically going to see weeks and maybe months, maybe years of just float charging, not being really asked to do anything except be there and be fully charged. So sealed AGM type batteries are almost always our choice for these backup systems. Now, if the system is actually being used, if we expect the grid to come and go, this is a foreign country, offshore or something like that, the grid isn't always available, and it will really get cycled, then wet cell batteries start to look better. Wet cells are cheaper, but in this case, wet cell batteries usually suffer short, ugly lives when they're put into backup service. They just don't like sitting around, never being exercised. Most of these backup systems, we recommend 4 of the 8 D size AGM type batteries. This gives you about 9.5 kilowatt hours of usable storage space. That's a reasonable size system for backup. The average American home burns about 20 kilowatt hours per day with no attempted energy conservation. So if they've got 9.5 kilowatt hours and they're in critical loads backup, that seems like it'll cover most folks pretty nicely. As you can see in the picture here, this is actually a battery pack on my own household system. It's about 2 feet by 4 feet. And I've removed the top of the battery box to take this picture. It is normally covered up. You don't want things dropping on those terminals. It gets way too exciting. Okay, review time. So, cost is $6,000 to $8,000 at a minimum. I would say honestly, for most customers, if you quote $8,000 to $10,000, you're probably going to be in the ballpark. These add-on packages are an easy upgrade for existing grid tie systems. And these are the easiest way to add backup to new grid tie systems. PV size is limited. We can get up to about 8 kilowatts with the Magnum systems, or up to about 15 kilowatts with the Sunny Islands. We have done larger systems. You don't have to back up all of the client's PV. Sometimes we drop an inverter or two on these larger systems when the grid goes down. So the customer gets 8 kilowatts of PV, still feeding into a system, and the rest of it drops offline. If this is an all-new system, one of the direct grid tie systems, the Outback, Xantrex, or Sunny Island systems are going to be a slightly lower cost package for them. So the direct battery systems range from 4 kilowatts to up to 80 kilowatts of capacity. 1 to 2 days of battery capacity is probably plenty. We want to use a backup generator if you want to add more days than that. And 3-phase system battery backup is possible, but it's pricey. Remote islands, eco resorts, places like this that are typically off-grid. Okay, and that wraps me up here, except to say, call us. We can design these. We do drawings. We do system designs. We do support. Okay, and Kathy, if there are questions now, let's hear them.
Yeah. Yes, we're getting lots of questions in. But thank you very much for the great insight, Doug. We do appreciate that. And I just also wanted to apologize for the technical issue before. We had some dropped calls. But I did want to go back and read Doug's bio because Doug, you've done some pretty interesting things. So I just wanted to give that a minute. Doug has worked professionally in the solar industry since 1985, doing installation, design, tech support, engineering, and product testing. He's been instrumental during that time in growing a couple of little mom-and-pop stores to national significance, such as Real Goods and DC Power Systems, Solgent. He has designed or supported many thousands of grid tie and off-grid battery-based systems, from simple 10-watt systems up to 1.3 megawatts. And Doug also lives his passion with his passive solar carbon-neutral home in Northern California, which is all electric, right down to the barbecue, which, as he says, PG&E usually ends up billing him at the end of the year, yearly billing cycle, as you saw a picture of his home in there too. So I just wanted to share that with you and give Doug a moment to grab some water there. But now, after all the information, our audience does have some questions, so we'll begin asking those. Remember that you can submit questions at any time in your GoToMeeting panel on your right. So we're getting lots in. So I think we'll begin with one here. A lot of people are asking if these kind of systems will work with microinverters. Can you answer that, Doug?
Oh, yeah. Sorry I didn't address that. Absolutely. As I said, the Magnum or the Sunny Island systems will work with any brand of inverter, and that includes micros. And in fact, Enphase, as a particular brand, has stated publicly that they have no problems with any of these backup battery systems like this. They're perfectly happy running through them. So not only will it work with microinverters, but the microinverter manufacturers generally support them.
Great. Another question here. One moment. They're coming in real quick here. In a grid-tied battery system, are the batteries only being charged by PV, or can the utility grid charge the batteries too, such as in applications in rural areas where the grid is unreliable?
Yeah. With the direct battery-based systems, the inverters are smart enough so that they won't let the utility charge the batteries unless there's been a power failure or for some other reason the batteries have been allowed to run down quite a bit. So under normal conditions, the system is going to let the PV recharge the batteries. If it's just an overnight thing, they'll recharge it with PV the next day. But if the power goes out for any period, then the first thing that the inverter is going to do when utility power comes back is run a float charge on the batteries and pop them back up. Be ready for the next outage.
Got it. Do the microinverter systems require going back through a DC inverter to the batteries?
No. Once you come out in AC, that AC from the microinverters is going to land on the critical loads breaker panel, AC breaker panel, and it's all AC from that point on. So no, it'll pass through the add-on inverter, but it passes through its AC, not DC.
Got it. Okay. Here's another one. They say every couple of weeks we switch to battery backup with PV just to test the system. Is this advisable to kind of stimulate the batteries and make sure that things do what they're supposed to?
I don't know if you need to test. These systems are stone cold reliable. But deliberately cycling the batteries, exercising them, is a really good idea. I try to do mine every couple of 3 months. I go deliberately switch off utility power to the inverters and switch off the PV and make the system use the batteries, until I get them down to, 50, 60% or so. Lead acid batteries, like to be exercised. Think of them like the muscles of your body. We all need modest amounts of exercise in order to stay healthy. And it's the same with batteries. So, yeah, if the folks can remember to, exercise them every couple of months, that's a good thing. Testing the system, I wouldn't worry about it. It'll be there when you want it.
Great. Are purely off-grid solar systems as expensive as these on-grid backup systems?
Generally, no. Now, much of that is simply because folks who are going into an off-grid situation are usually a lot more careful about their electric loads. They know that electricity is going to be expensive and limited, so they choose appliances with a bit more care. So, we see off-grid houses simply consuming less electricity, which makes the systems less expensive. However, I have done some off-grid systems that were enormously expensive just because, these were rich folks who knew no bounds, and, no was not an answer they would accept. So you make the system as big as the customer wants. Sometimes that's ridiculous.
Always, doing what they ask. I understand. Here's a good one. Are there any particular safety requirements for these type of systems, Doug?
I'm sorry, that got garbled a little bit. You run that by me again?
Yeah. Are there any particular safety standards for these type of systems?
Spacing?
Safety, as in being safe.
Safety. Okay.
Mm-hmm.
Batteries have to be enclosed so that the terminals are protected. Sealed batteries don't vent, but the building code does not recognize that. They just see all batteries the same, whether they're wet cell or sealed. So, the batteries need to be in an enclosure that vents to the outside. So,
oh, sorry. Do you have anything to add?
You cleaned me out.
Okay. Okay. I just wondered. Okay. Kind of going along with that. what about the maintenance of batteries, such as venting, equalizing? Do the inverters, do they assist with these tasks?
So long as we're using sealed batteries, maintenance is pretty low key on these. About once a year, you need to snug up the battery terminals. The terminals are lead. Lead is a soft metal, and it gradually creeps over time. So we need to snug up the terminals and wipe down the tops of the batteries with a damp sponge. So 20 minutes of maintenance once a year, that's about it.
Did you discuss nickel iron batteries at all?
You're garbling on me, I'm sorry.
Oh, okay. Did you discuss nickel iron batteries at all?
I didn't, mostly because they are not a terribly viable option for solar-based systems. Nickel iron has the advantage of long life expectancies. Some of these batteries can last 50 to 70 years. The disadvantage is they got horrible efficiency on them. Half the power that you throw at the batteries, at a nickel iron battery, is going to disappear on you. They need regular routine overcharging. So if you've got a hydro turbine, or you live in North Dakota with a big wind turbine, nickel iron might be for you. You know, those folks with power to burn, nickel iron is a nice choice. For the rest of you, you know, living on solar, don't even think about it. You know, you can't afford them. They'll just, your power's just going to all disappear. There.
Got it. I know I'm throwing a lot at you here, but they're coming in quickly here. We have some good ones. This is kind of about asking what happens when the batteries are full and overcharging. You said that charge controllers charge the batteries at, they have limitations. The inverters don't allow more than a certain amount to go into the batteries. So what happens once they're 100% full, and what are the kind of the dangers of overcharging?
Okay. So as long as utility power is available with these systems, the inverter is going to hold the batteries to, you know, a standard float charge level, you know, a voltage that the batteries can stand, you know, 24/7. If the utility fails, now we don't have any place to dump that excess power, and the charge controller finally gets to be a controller, and it gets to limit how much power goes into the batteries. So it will bring the batteries up to, you know, a couple volts, up to 56 volts or so on these systems. But then the charge controller cuts in and it starts limiting how much power goes to the batteries to prevent overcharging. So that's how it works when the utility goes down.
What about hybrid systems when you have a combination of PV or wind or hydro? Are there any different considerations for those?
Each power source is probably going to have its own sort of charge control, you know, for it. They will all operate in parallel, and as long as they're all designed to charge a 48-volt battery pack, that's fine. We can have multiple inputs to the battery, and as long as they're all programmed, you know, to maintain the same voltage levels, that's fine. They'll all get along happily together.
Got it. Here's a question about the draining of batteries. What's the maximum that the batteries should be drained?
Most of these deep cycle batteries that we use for solar can tolerate 80% depth of discharges. That's you're using 80% of the power. You know, there's 20% left. That's about the max, and even that is something you don't want to do, any more than you can help. On a daily, sort of cycling, say this is an off-grid system, we aim for using more like 20 to 30% on a daily basis. So 80% is the max. 60 to 70% is where we usually design the systems, and leave a little cushion for emergencies.
I think we have time for a couple more here. What's the best way to kind of clean and prevent the gray-green salt-like stuff, for a technical term, forming on wet cell battery terminals?
Okay, the way to prevent it from forming is to keep air away from the battery terminals. You do that with grease or with the spray-on stuff that your Friendly Auto Parts store provides you. So, batteries are going to vent some things besides water vapor. And some of those sulfur compounds like to attack copper, so you get corrosion at battery terminals. So when you first install the terminals, once it's snugged down, just swab it with Vaseline, grease, whatever. It doesn't particularly matter what it is, just so long as we put something on there that's a barrier to those fumes coming out of the battery. And you won't have any more terminal problems.
Okay. Well, I think we have time for one more here. And I think we'll go with, is there a way to add battery backup to an array with an existing line side connection?
Yeah. Doesn't make any difference what's going on the AC landing here. We can still basically insert the add-on system between the AC connection and the critical loads panel. It doesn't really change anything.
All right. Well, again, I think that's all we have time for today. But I did learn a lot, and I hope you did too. And I know there's a lot of questions that we didn't get to, so if we didn't get to it, or if you have additional ones, feel free to contact Doug on your own. And again, this webinar will be emailed to all registrants, so you can view it again at your convenience. And I would like to thank Doug one more time for being here to share his excellent expertise with us. We really appreciate it. And also thanks to everyone in our audience for listening and asking such great questions. Your input makes for a great discussion. And I hope you enjoyed the presentation, and we invite you to join us for more Solar Power World webinars. Thank you, everyone.